Great. Welcome, everybody. We are beginning with another semester of the One World YoungStatS webinar series. I note at the start that the webinar series is part of the Young Statisticians Europe, part of the YoungStatS project of Young Statisticians Europe initiative, part of the Differential Association, and officially supported by Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics, IMS. Today we will discuss a very interesting and relevant topic, I would say, regularization by noise for stochastic differential and stochastic partial differential equations. We have luck to have four great speakers: Helena Kremp of Freie Universität, Berlin, Germany; Lucio Galeati of University of Bonn; Lukas Anzeletti of Université Paris-Saclay; and Igor Honoré, Université, Claude, Lyon. I apologize if something was misspelled, and as discussant and organizer, I would say, of this webinar, Oleg Butkovsky, researcher at Weierstrass Institute for Applied Analysis and Stochastics in Germany. So also due to time reasons, you will hear more in the presentations. I invite Helena Kremp to start with her presentation. Thank you. Each presentation will be about 20 minutes long, and please insert your questions in the chat. They will be put during the presentations or live. The webinar is recorded and live streamed on our YouTube channel. Thank you.
Thank you. Let me first share the slides again. Yeah. Well, thank you for the invitation, Andrea and Oleg. I'm pleased that I'm able to speak here at this webinar. So I will speak about basically different weak solution concepts for singular Levy SDEs. So there are no SPDEs, but SDEs in this talk. And this is joint work with my PhD advisor, Nicholas Butkovsky. So as I'm the first talk, I should maybe introduce the phenomenon of regularization by noise. So if you consider an ODE and delete this Brownian motion here, then if the drift is beyond Lipschitz, your ODE might not be well posed. It might not have a unique solution in general. For example, you could take the square root and you start the equation in 0, then you would have several solutions. Actually, solution would be 0 plus minus t squared or combinations thereof. So you clearly don't have uniqueness. And regularization by noise means that if you add this noise, this Brownian noise, then you restore well-posedness of the SDE. And the first result in that direction was by Zvonkin and Veretennikov, where they could prove for bounded and measurable drift already probabilistically strong existence and uniqueness of solutions. So this was basically by proving first weak existence by the Giersanov transform and then pathwise uniqueness via the so-called Zvonkin transformation. And then there were like various other works in that direction. And the credo is more or less that you have more regularization by adding rougher noises. So in the sense that adding rougher noises, you could put more rough drifts V. And you can make use of this more regularization. And there are also several works in that direction, where the list is also by no means complete. And in general, you can even prove strong solutions even for distributional drifts when your noise is rough enough, like taking fractional Brownian motion with a low Hurst parameter. And Lucio will also talk about this. But in this talk, instead of Brownian noise, we add alpha stable noise, and there we have less regularization as by putting Brownian noise. So the alpha stable process has as a generator this fractional Laplacian to the power of alpha half, and the alpha is in the pure stable case strictly less than 2. But we will need to take it greater than 1. So in this talk, we actually consider such SDEs where the drift can also depend on time, but is continuous in time, and then in the space variable, it's a distribution, a base of distribution. And we put alpha stable Levy noise. And then what results do exist? Actually, in the one-dimensional case, you can still prove strong existence and uniqueness, but as soon as you go in higher dimensions, or when you lower the beta, you only get weak solutions. And and in fact, you can go down to beta greater than 2 minus 2 alpha over 3, which we call the rough case. And in this case, you have existence and uniqueness of martingale solutions under an assumption on the drift, which we call enhanced drift. And we will get to that, what this means in general. And as an example, you could put a periodic white noise, a typical realization of a periodic white noise as a drift, and this would be covered in the rough regime. So we get martingale solutions. So this would be an example one can have in mind in the rough regime. Now, what is this martingale problem? In general, if you have a nice drift, smooth drift, then your diffusion has this generator here, where this L alpha is the fractional Laplacian. And from the classical theory, we know that the law of the solution solves the martingale problem for that generator, and it's enough to formulate the martingale problem for smooth test functions. And this already characterizes the law then. But the problem when I take a distribution V is that when I multiply a test function or the derivative of this test function with the distribution V, then what comes out is also a distribution of the regularity of V itself. So this evaluation of the generator in this test function will be a distribution, which is a problem for the martingale problem. So what we do is that we impose that this evaluation is equal to a function itself, an L infinity function. So we say that a probability measure solves the martingale problem if for all such L infinity functions and all nice, smooth enough terminal conditions, the process M is a martingale, where M is given by this expression, and U solves the Kolmogorov equation with right-hand side F and terminal condition UT. So this would be a singular martingale problem, and it characterizes the law uniquely. It will, the process that solves the martingale problem will be a Markov process, and we transformed the problem into solving such a singular Kolmogorov equation. So why does the equation have a solution? So the Young case, so the mild solution is given by this formula, where P as the semigroup denotes the semigroup associated to the fractional Laplacian. And then it's quite easy to see that if V has regularity beta, then the solution has regularity alpha plus beta by the so-called Schauder estimates. And also you can see that it is Hölder in time, so alpha plus beta over alpha Hölder in time with values in L infinity, or it is Lipschitz at time with no increasement in space. So this is where your solution lives. And now, of course, you cannot take arbitrarily rough distribution V, because you need to make sense out of this product. And the product is well defined if the regularities sum up to something strictly positive. And this is exactly this Young regime. So this regime on beta where this product is well defined. Now, as I said, we also want to consider beta in the so-called rough regime, so rougher than this. And this we can do by assuming more on our drift and by imposing a so-called para-controlled Ansatz. So para-controlled Ansatz just means that we say our solution should have a specific structure. It should look like the solution is given by a more regular part, U sharp, plus a part that looks like this one, like JT of V. And then we are basically left to define the product of V times this derivative of the more regular part, which will be well defined also for lower beta because this guy, the U sharp, is assumed to be more regular, and the product of V times this guy here. And this is our assumption on the drift. So we assume that those resonant products exist, whatever this resonant product is. We assume that this product of V exists. And then we can have a solution in this para-controlled solution space also for lower beta. And the solution map will be continuous, and we can also generalize. So this was for a nice enough, smooth enough terminal conditions and right-hand sides, but we can also generalize to singular para-controlled terminal conditions and right-hand sides, obtaining a solution which will have a blow up. So it's possible to generalize this, and it will be relevant in one part of the proof later on. Yeah. So when we have a solution to the Kolmogorov equation and we have continuity of the solution map, we can show that it also exists a unique solution to the martingale problem for the generator. And yeah, as we defined it before. And how would one prove such a result? Of course, one considers the strong solution of the SDE with smooth drift approximating the distributional drift V. So this one, Xn, and then prove tightness of the laws of these Xn. And moreover, prove that the martingale problem is uniquely solvable. Then the limit will solve the martingale problem. And the tightness is exactly obtained by that lemma here, which gives the moment bounds on the drift terms, and which also shows that the limit drift term will be Hölder with regularity alpha plus beta over alpha. And this is exactly the Hölder regularity that we saw for the solution of the Kolmogorov equation, like 2 slides before that one. So this is how we see that this drift term will have that regularity. Now, why? So basically, if one thinks of what would be a natural weak solution, one would directly more or less write down this one. So we call a weak solution a tuple X and L, where X is given by this drift term Z plus L plus little x, which is the initial condition, where this drift term Z is approximated by the smooth drift terms for a sequence that approximates B. And this Z has this regularity that we saw before in the lemma. So if we write such a weak solution concept down, then we see that it is well posed in the Young case. Actually, it is equivalent to martingale solutions in the Young case, and that was already considered in the work by Oleg and co-authors. But, and this was the motivation for this work, it won't be well posed in the rough case. And the reason is it will be non-unique in general. And the reason for that is that this resonant product does not need to be unique. So I can find, even in one dimension, I can find two sequences such that this mixed resonant product, where I put here the sequence and here the V itself, that this product converges to two different limits. So for one sequence converges to that limit and for the other one to that limit, and they don't need to be equal. And by that, I can show that I would obtain two different solutions in law. So this was the motivation to somehow define a weak solution concept that is equivalent to martingale solutions, also in the rough regime, and in particular unique. And for proving that a weak solution is a martingale solution, one comes to a point where one needs stability of certain integrals. So when U is a solution of a Kolmogorov equation, then and I approximate that solution, and I also approximate this drift term Z that we saw before, then I want that this integrals converge now too. But if I count the regularities in the rough case, so I count the time regularity of this derivative of U and the regularity of Z result we saw before in the lemma, then the sum would be less or equal than 1. So I cannot just apply the skewing or stochastic skewing to these integrals. But instead, what we do is that we remember that the solution of such a equation, Kolmogorov equation, is actually controlled, and we more or less can enhance Z in a rough path manner such that this integral is stable. So we define a so-called rough-stochastic integral, which we can define for a rough-stochastic integrator Z bar, and a stochastically controlled process. And and then stability we will get from the stochastic skewing lemma by Coallet. So in general, this is what we do. I will not go into great detail because of the time, but as I said, we have a stochastically controlled process. So both are stochastic here, and that one is controlled by the process A. And these both Z are basically formally the iterated integrals of A integrated against Z. And then we can find this integral by the stochastic skewing lemma. So the bounds are exactly such that they match in the stochastic skewing. And in fact, we can prove for a para-controlled solution that it will be stochastically controlled by this process A. And so this basically needs just the regularity of the para-controlled remainder and the regularity of the process X itself, where we need to be a bit careful that we don't exceed moment bounds greater than alpha, because the Levy process only has moments with exponent less than alpha. But this works out if we only assume in L2, and the solution is stochastically controlled. And moreover, we need to assume that these iterated integrals, both Z, that they satisfy the bound such that both Z is a rough stochastic integrator. So this is an assumption that we need to put into our weak solution such that we can prove that they will be equivalent to martingale solutions. So when the Z corresponds to this drift term, the ZA corresponds to this product that we needed to assume. So what this this solution concept looks like this, we now have a triple XL bold Z that we call a weak solution, where again X is given by Z plus L. Z is this drift term that it is approximated as before by the smooth drift terms, and bold Z are these iterated integrals. And they satisfy the bounds that are needed such that this guy is a rough stochastic integrator. It looks a bit scary, but it's actually just that we assume that this guy is a rough stochastic integrator. And it's worth noting that if beta is in the Young case, so if it's actually more regular, then this concept collapses to this canonical weak solution concept that I showed before. So it's a generalization, yeah, it's basically a generalization of the one in the Young case. Yeah, and then with this, then we can show that indeed a rough weak solution solves the martingale problem. And this is where the stability of the rough integral comes in. So if we apply the E2 formula to a solution of the Kolmogorov equation, we want that this blue part here is a martingale in the limit. And therefore we want that this remainder, this orange remainder, goes to zero, stability that we proved before. And for the other direction, that a martingale problem is now a rough weak solution, there it is basically everything more or less straightforward, except of the bound on bold Z. So the convergences of this 1 and 2, these convergences follows from scored representation theorem and considering the right solutions of Kolmogorov equations. And the bounds, these bounds follow basically from the lemma. So the sigma is again this Hölder regularity of Z. And the only hard part is showing that bound, because this is strictly greater than sigma to make this work. And this requires to solve the Kolmogorov PDE also for singular terminal conditions. This is why we generalize this. And yeah, but then when this hard part is proven, then the martingale solution will be a rough weak solution. Yes, so we have equivalence, and in particular that this rough weak solutions is a weak solution concept that is well posed and unique. And then maybe a small extra thing is that for rough weak solutions, we also have an E2 formula. And instead of this dz, we have this d enhancement of z. And yeah, and this additive functional is actually an additive functional of this Markov process, but the functional is a distribution. So this guy will also need to skew. So it's defined by also the stochastic string. Yeah, and this is where I wanted to end the talk. Thank you very much.
Okay, thank you a lot. Clap, clap, virtually. Are there any short questions in the chat? There was nothing still.
Maybe I can start with some questions and then...
Oleg, maybe we wait for this for you and for the discussion, if you agree.
I think there's a hand. I saw something.
There is hand. Okay, Jane, Link, please. Yeah, unmute. Unmute yourself. You're probably able to. Yeah. Please.
Can you hear me?
We hear you.
Yes.
Okay. So thanks for this nice talk. I I'm not sure if I got the point. My question was, you just build this equivalence between the martingale problem and the weak solution, rough weak solution. And so then in this sense, the one could show the existence of either martingale solution or rough weak solution. I just was wondering, could you say anything on the uniqueness?
On the uniqueness for rough weak solutions?
Oh, yeah, right. Or the uniqueness of the martingale solution.
Yes, so both are unique. So the thing is, for martingale solutions, we proved the uniqueness. Mm-hmm. So uniqueness in law, of course. Mm-hmm. And for rough weak solutions, we proved the equivalence to martingale solutions. So then they are also unique. Yes.
Okay, so then
this was basically,
I mean, so for showing the uniqueness, whether I'm just wondering whether you use the uniqueness of the corresponding Kolmogorov equation and then show the uniqueness of the martingale solution. Is that the idea behind? Or
you have the uniqueness of the Kolmogorov equation, mm-hmm. but what is behind the uniqueness of the martingale problem? That is basically, yes. So the argument for the uniqueness of the martingale problem is the general one, as if you would consider, But so of course you will need that. That you have uniqueness of the Kolmogorov equation, and you also use at some point the continuity of the solution map of the Kolmogorov equation. But it's basically, so the argument for the uniqueness of the martingale problem is the Ethier-Kurtz argument. So there's nothing new basically inside that.
Okay, thank you.
Yeah.
Okay. Thank you a lot again. I suggest we move forward now. Helena, I will ask you to unshare.
Yes.
Great. Thank you. So next one is Lucio Galeati of University of Bonn, who will speak about advances on simpler SDEs with fractional noise in subcritical regimes. Lucio, please, the floor is yours. Thanks again for a good presentation.
Perfect. So thank you very much for having me here. Thank you for the presentation. So what I'm going to present is based on a joint work with Mategar and Chair, and it's actually an archive preprint we uploaded last July. So as Helena already introduced, I mean, also in this talk, the main player will be SDEs. And again, the main game I want to play is to understand if whenever I consider an ODE and I insert an additive noise into it, this actually basically improves my solution theory in the sense that the original ODE might either don't have solutions or have more than one of them, and I would like both these pathologies to disappear when I introduce my process W. So again, let me just make a quick recap, which Ellen already mentioned. Whenever our drift B is Lipschitz, all life is fine. Essentially, for any initial data, we do have existence and uniqueness of solutions with or without noise. But as soon as we try to go a bit below that, actually either existence or uniqueness might fail. So for instance, for alpha between 0 and 1 excluded, there are examples of infinitely many solutions starting from the same initial data. And if we go even below, the situation gets worse. So for instance, for bounded measurable drifts, one can show that non-existence can happen. And for negative regularity, it's not even clear what is the meaning to give to the equation, because now this function cannot be pointwise well-defined. So what I would like to understand, some of the main questions I would like to touch in this talk are, first of all, to at least characterize some large classes of processes which do possess a regularizing effect. So in Helena's talk, this was given by Levy or stable processes. Here it will be actually fractional Brownian motion. And then the next natural question is to understand essentially what we can hope for. Essentially, what are the mildest possible assumptions on our drift B, such that for a given W, this equation is well posed. And finally, even after having established existence and uniqueness, which is an extremely interesting question of its own, one would even like to understand better what is the behavior of solutions. So for instance, some natural questions would be to understand whether solutions do form a regular flow, where regularity is in the sense of dependence from the initial data in the space variable, or one could even ask if solutions X inherit the same regularizing effect as the driving process W, and so on and so forth. So as I mentioned, in this case, the class of processes that we consider are fractional Brownian motion. So there are a fundamental family of processes indexed by a parameter h between 0 and 1, called the Hurst parameter, which have the features of being center Gaussian processes with the following prescribed covariance. So modernly, they will introduce by Mandelbrot and Van Ness, but also before, for instance, by Levy and Kolmogorov and other authors. And as the name suggests, they are a natural generalization of Brownian motion. Brownian motion coincides with the value h equal to 1/2. At the same time, there is something we lose in this generalization, as in fact, for h different than 1/2, these processes are not Markovian nor semi-martingales. But still, they do share many similarities. So for instance, one can show that there are almost h-holder continuous, but nowhere exactly h-holder continuous. And another fundamental feature, which will be the source of regularization in this talk, is actually their local non-determinism. So basically, in the standard Brownian case, we know that if we take the increment Wt minus Ws, this is entirely independent of the previous history of the process up to time s. This is not going to be, again, true in the fractional Brownian case, and this is one of the sources of its non-Markovianity. But one can at least say is that if we look at the increment Wht minus Wh of s, this increment will contain a Gaussian component which is independent of the past up to time s, and which is sufficiently large, in the sense that the variance of this component can actually be lower bounded by a constant time t minus s to the power 2h. So this is exactly in line with the case h equal to 1/2, where one can just take the constant to be equal to 1, and actually here is an exact equality. So somehow the idea is that even if we know all the history of the path up to time s, we cannot predict accordingly what will happen at time t, which actually makes the path chaotic and its trajectory is very oscillating. Finally, this is a self-similar process, which is also the reason why Mandelbrot and Van Ness were studying it. And in fact, I will further generalize this class by allowing also values of h strictly greater than 1 in the following way. Basically, recursively, I can find fractional Brownian motion parameter h when h is greater than 1/2 as the integral in time of fractional Brownian motion parameter h minus 1. And this is a good generalization, at least in the sense that all these properties I listed here actually do carry on with this new definition. So this is a graphical representation of what these paths are doing, at least for h ranging between 0 and 1. So on one end, you see that as h gets smaller and smaller, the oscillations gets faster and faster and wilder. And basically, it starts presenting more and more spikes, the trajectory of the path. And the idea behind why regularization should happen in this framework is that oscillations lead to cancellations, basically. And the hope essentially is that if the driving process W has these wild oscillations, then any solution to the related SDE should inherit them as well, which should be the key for its own uniqueness, essentially. But again, let me stress, this is not Markovian nor a martingale process. So all the standard stochastic analysis tools, for instance, some of those we saw in Helena's talk, so like the martingale problem formulation or relation to PDE methods, for this class of processes are completely lost. And in fact, one has to actually introduce new ideas. So here, new is a strong word because there is research on this ongoing from at least 20 years, but at least let's say much less classical tools than the ones that are taught in stochastic analysis courses, which are related to Ito calculus. And there is at least one thing one can do before going hands-on onto computation, and so actually make an educated guess of what we can hope for. And to do so, one can actually do a rescaling argument, which is actually relatively simple. So we do know that our driving process WH is self-similar with a certain parameter. So what we can try to do is to say, well, assume we have any given solution to the SDE, we can try to apply the same scaling to the solution itself. And so what happens is that the new rescale function now will solve again an SDE of the same type, but where now the drift itself has been rescaled. So the idea is really that we're just zooming in. We're really looking at, on short scales, what the process is doing. And so naturally, a necessary condition in order for some regularization to hold is that as we zoom in closer and closer, the noise part should be stronger than the nonlinearity represented by the drift B. So somehow what we expect is that the regime where things should work well is the one where, as we zoom in ideally infinitely, so we set lambda going to 0, the nonlinearity will disappear. And one way to look at this is to say, well, okay, assume B lives in a certain regularity class, which for me will be in the class LQ integral in time, C alpha in space. Now I can look if the rescale function obtained in this way converges to 0 as lambda goes to 0. And this is a direct computation. One can actually obtain that this norm is equal to lambda to a certain exponent times the original one. And so what I will call the subcritical regime, so where we can hope for a good solution theory, is when this exponent here is actually strictly positive, so that the overall quantity is infinitesimal as lambda goes to 0. But let me stress, this is just an heuristic argument. It's nowhere rigorous, and we already saw in Helena's talk that actually it's not always so easy to pull this off. Like in the Brownian case, h equal to 1/2, if I take q equal to infinity, or even I just take B to be an autonomous C alpha drift, this argument would predict here the condition alpha greater than -1. We saw before that already going beyond the Young regime, which corresponds to alpha greater than -1/2, actually requires a lot of care. And even what is the correct notion of uniqueness is not trivial at all. But in any case, I mean, once we have this educated guess, we can essentially try to test it against what is already known in the literature. And again, I can only mention very few authors. Of course, there are many other people, but we can start with the most traditional case, which is the Brownian one. So one of the fundamental results in regularization by 9, one of the landmarks, was the one by Krylov and Rockner. They essentially showed existence and uniqueness, strong existence and uniqueness of solutions whenever B satisfies a certain integrability condition, when it's LQ in time, LP in space, where the parameters satisfy this relation, 2 over Q plus D over P is strictly smaller than 1. What is really interesting here is that actually, if we embed LP into the corresponding C alpha space, which is given by alpha equal to minus D over P, actually this condition is exactly the one suggested by the subcritical regime. So there is also some confirmation that this subcritical regime is actually giving us at least partially good hint of what is going on. And 2 other results I want to mention because I will connect to them later on. Davy was also the first one instead to observe that in a more regular case for a drift which is measurable and bounded, one can even show a stronger form of uniqueness, path by path uniqueness. I will not give too many details here. I think Lukas will talk about it. And on the other hand, starting with the work by Flandoli, Gubinelli, and Prola, people realized that one cannot only treat SDEs, so regularization by noise for ODEs, but actually one can also use this to obtain regularization results for transport equation. Transport PDE is strictly related to them. Then, okay, the first results, I mean, among the early results for fractional Brownian motion, there are at least 2 ones that have to be mentioned. The first one is by Noalart and Oknin, early 2000s. They established under suitable conditions strong existence and uniqueness in the one-dimensional case. And their proof heavily relies on Girsanov transform, which is a tool which is also available in the fractional Brownian case. And then another landmark result, which also Helena already mentioned, is the one by Catania and Gubinelli from 2016. So here they showed in any dimension that if we take a drift B, which is C alpha, under the assumption that alpha is greater than 1 minus 1 over 2h, strong existence and uniqueness holds. Let me stress, this is also particularly surprising because here you really can take alpha to be a negative value as long as this condition is satisfied. So, I mean, B's can be purely distributional, and even making sense of the equation is not trivial at all. Still, one can actually solve it in a very strong sense. And then, I mean, okay, this is my personal classification. There is a class of more modern results, and I call them like this because they all have the common denominator of being heavily based on the use of the stochastic swing lemma, which is a tool that Coale introduced in 2020. So among them, there is, for instance, the work by Oleg, together with Konstantinos Aerotis and Mateger and Cher, where they do obtain strong rates of convergence for Euler-Maruyama schemes. Then there are the works by Atreya, Butkovsky, Lem, Mitnick, and by Lukas and Richard and Honoré, where, loosely speaking, they are able to actually reach the equality here, alpha equal to 1 minus 1 over 2h. I'm a bit oversimplifying here. And finally, there is a work by Mate, published in 2022, where it was the first one to actually extend these considerations also to the case of values h greater than 1, still recovering the Catelian-Gubinelli condition. Let me recall this subcritical regime, which I mentioned before, for q equal to infinity is given by alpha greater than 1 minus 1 over h. So we are actually far away from it. There is a coefficient to one, an extra factor 1/2 here, but we already have many interesting results. And with this preparation, I can now actually state what is the results we obtain in the joint work with Mate. So here now we can consider any value h between 0 and plus infinity, excluding natural numbers. And we look for drift B in the regularity class LQC alpha. So what we were able to show is that strong existence, pathwise uniqueness, and path by path uniqueness do hold for the SDE in the subcritical regime. So under the condition alpha greater than 1 minus 1 over HQ prime, under the additional condition that Q is between 1 and 2. So this is the subcritical regime. This is an artifact of our proof, conjecturally. So still it's interesting because we now really reach a subcritical case. On the other hand, let me point out, whenever Q is less or equal than 2, actually this quantity is necessarily greater or equal than 1 minus 1 over 2h. So in terms of space regularity, in terms of which values alpha we can allow, we're not going beyond the Catelian-Gubinelli theory. Where we are improving and where we expect that we cannot improve any further is that we can decrease the time integrability in Q. So B is allowed to depend on time and just in a merely integrable way. In any case, not only would we establish existence and uniqueness, we do show that the SDE admits a stochastic flow of diffeomorphisms. So the solution map essentially as a function of the space variable is C1 with C1 inverse. And we also present stability estimates. So if you give me any two solutions associated to different initial data and different drifts, both living in this regularity class, then I can control any moment of the supremum norm of the two distinct solutions on any arbitrary large time interval 0 capital T by a certain constant, which depend on all these parameters, times the distance between the two original initial data and the distance between the two drifts. And what is interesting here is that although well-posedness comes in the regularity class LQC alpha, instead, stability will come in 1 degree of regularity less. So the difference of the two drifts only has to be measured in LQC alpha minus 1. Let me point out, this result is already of interest on its own. It also has practical application when actually developing numerical schemes for singular drifts. Because the idea is like, you cannot directly run the scheme for a drift B, which can be unbounded, because as soon as your solution lands too close to it, this will become too much of a source of error for the numerical scheme. But what you can do is to first modify the drift or truncate it, or use any approximation, and then run the argument for that truncation. And if you do that, the first error you commit by this replacement is something you can control with this kind of estimates. And this argument has been run, in fact, by several authors by now. So these are the main results I want to present, but we do also obtain some other ones. So for instance, we're also able to treat in our analysis distribution-dependent SDEs. So what I mean here is that we can consider a class of equations where now the drift B not only depends on the solution itself X for its position, but also on the law of the solution at time T. And in particular, we can cover the so-called convolutional case. So the case where this capital B drift as a particular structure, which is given by two kernels, one only depending on the position X, and the other one, G, also depending on the law in a linear way through a convolutional structure. And in particular, we can solve these equations in a strong sense whenever F and G are again in the prescribed LQC alpha regularity class. Next, what we were able to show is that solutions to these SDs are Rho regular. So Rho regularity is a concept that was introduced by Catelian-Gubinelli. Unfortunately, I don't have enough time to explain it properly here. let me just say it's a way of measuring both the regularity of the path and the regularizing effect it has on the equation. So in the original paper by Catalini and Gubinelli, they were able to show that fractional Brownian motion is very regular for any rho smaller than 1/2h. What we show here is that also solutions to the equation driven by FBM enjoy exactly the same property. And it can also be shown that this, up to reaching the critical equality, is optimal. One cannot reach values greater than 1/2h. We then have a small result in which now, if we in some sense weaken the condition, the regularity condition of the drift, at least in the sense of the alpha value, I mean, we allow for more generous regularity in time, but if we weaken the regularity on space by only prescribing alpha greater than 1/2 minus 1/2h, we're still able to establish existence of weak solution. So the price to pay here is that really, this is just existence. We do not know whether these solutions are strong. We do not know whether these solutions are unique in any way. Let me also recall, we are still far away from the critical regime. I mean, the subcritical should be alpha greater than 1 minus 1/h. And instead here, I mean, we're getting a bit closer, but there are still a lot of questions and a lot of answers missing. But at least we can confirm that the so-called, I mean, this identified subcritical regime is the best we can hope for. I mean, we do not know whether on the positive side we can cover it entirely. At least we do know that on the negative side, there is no way of reaching it any farther. In the sense that we provided in the paper also examples of drifts which are LQC alpha, with alpha not satisfying the opposite inequality, so smaller than 1 minus 1/HQ prime, and for which either uniqueness in low or pathwise uniqueness fail. So these are the main results on the SDE. Since this is a webinar also on SPDs, I also want to shortly discuss the results we obtain instead when treating transport and continuity equations. So in this case, these are two classes of SPDs, so the transport one and the continuity one here, which are essentially dual to each other. And they also both have a very well-established connection, at least formally or in the regular regime, with the underlying SDE through the so-called use of characteristics. So in this case, again, I will impose my main driving assumption on the drift B of regularity LQC alpha. But in the case where alpha is smaller than 0, to simplify our life, we have to impose a bit more conditions because otherwise making sense of these products is a bit nasty. So in the truly distributional case, actually we'll at least require my B to satisfy some suitable local integrability assumption. So it's still actually at least locally bound, I mean, not necessarily locally bounded, but a measurable function. It's not truly a distribution. It's not a Dirac delta. That's okay. So I will impose additionally for alpha smaller than 0 that it has an integrability with respect to a parameter R. And what we were able to show is, in fact, again, well-posedness of these two equations. So more precisely, if you give me any P which is strictly greater than R prime, the conjugate exponent of R, then for any initial value U0, which is in a Sobolev regularity class, W1P, there exists a strong solution to the transport equation. And this initial Sobolev regularity is propagated by the dynamics. So this will be almost surely in an infinity W1P. Moreover, path-by-path uniqueness holds for the SPD in the class of these regular solutions. Similar statements also holds for the stochastic continuity equation. The only difference now is less regularity on the initial data. So again, same assumption, P greater than R prime. Then if you give me any initial measure mu0, which satisfies an LP integrability in space, there exists a strong solution to the continuity equation for which this LP integrability is propagated over time. And again, path-by-path uniqueness holds. So this concludes the exposition of all the main results I wanted to mention here. So far, I haven't given any details of proofs. So let me just very quickly comment on at least what are the key ideas that need to enter in this analysis. So the first one, which was already mentioned several times and also in Helena's talk, is the stochastic swing lemma. It was first developed by Koale in 2020. There are now many versions. It's a very elastic tool, like classical sewing. In our analysis, it answers in a very general way whenever we need to basically define in an abstract way what are processes of the following form. So we have integrals in time of a certain function f evaluated along basically the WH path perturbed by an additive perturbation. And the key point is that this in definition, which will be perfectly fine if f is a smooth function, is only formal because I need for this to make sense whenever f is a distribution. And stochastic skewing allows to do so under suitable assumptions whenever theta is a slowly varying perturbation of WH in a certain sense. And the second idea that has to enter the analysis, and this really, for me, it was a fundamental intuition by Mate in his paper now published in 2022, is that really you can come up with the right kind of a priori estimates for solutions to this kind of SDEs, which do exactly fit this description. So what one can show is that any solution X will actually decompose as the sum of a term theta plus the driving noise WH, where theta satisfies this kind of inequality. So it's a bit technical, but the reasoning is the following. Basically, one tries to understand if you give me the path theta time t, how well it can be predicted by knowing all the previous history up to time s. And the way one measured this is by actually, okay, taking the difference of theta t minus the best predictor up to time s, taking the distance of this guy, and again, taking what is the best prediction for this quantity. So what one can show is that this quantity is actually controlled by, okay, what is a so-called control to the power 1 over q? These are kind of objects that naturally enter whenever one applies skewing or stochastic skewing controls. And times t minus ace to the power alpha h plus 1 over q prime. And this exponent here, and this is by no coincidence at all, under the subcritical regime which we work on, actually is always an exponent strictly greater than h. So this is truly what I mean by slowly varying perturbation. The regularity of this guy is always strictly better than the regularity of the fractional Brownian path, which can be at most h. And okay, so these are the main ideas I wanted to expose, and this finishes my talk. So thank you for listening.
Thank you a lot. Again, clap, presentation. Are there any questions in the chat, or you can raise your hand? We have time for 1, 2 short ones. I will ask a short one and then let's continue. Could this be applicable to also generalizations of the fractional Brownian motion? Say in one side there are, I think, fractional and dimensional Brownian motions and so on, and on the other hand, say fractional Levy and other processes.
Yes, so that's a very good question. So yeah, like the main tools which enter in my analysis, in fact, is this fundamental property of local non-determinism. And more precisely, actually, we need a double-sided bound. So we need a bound on this variance greater or equal than t minus s to the power 2h, and also being less or equal than another constant I t minus s to the 2h. As long as I have these conditions, this analysis will go through, and this in particular is true for other versions of the fractional process. So Levy type fractional Brownian motion will as well satisfy these conditions. So in that sense, yes, one can generalize this even further. On the case of n-dimensional fractional Brownian motion, so if what you mean here is, if I understand correctly, is the field. You mean something which is indexed not on 0t, but on 0t to the power n, for instance.
Yes, yes.
Yes, there I don't have any precise answer. So I would definitely expect that these kind of processes have a regularizing effect. I think there are already some partial results in this direction. For certain class, for instance, of weight type PDEs, I think also Noalart and Oknin already accomplished that, partially using Girsanov. The problem there is that even just the notion of local non-determinism is not so clear actually which is the right one. So I mean, local non-determinism was first introduced by Berman and then by many other authors, also Pitt, Xiao, and so on. In the 1D case is, roughly speaking, well understood which are the right definitions, although there are still multiple ones. In the multidimensional setting is much more difficult. There is, for instance, sectorial local non-determinism. There are other versions. I do not know exactly how they can be used in order to obtain this kind of regularization results, although I would expect that there should be some way of exploiting them.
Great. Okay. Thank you. Thanks. Also, in the interest of time, I suggest we move forward. We will have discussion.
Maybe we should
later.
let Avi ask a quick question. Here, the question.
Avi, if it is really quick, please. Yeah, please.
Yeah, it will be quick. And if the answer is long, then don't worry, Lucio. Super nice talk. Just back to the transport equation or the transport continuity equations. Can you just explain how, just maybe you said it, I just missed it, how you make sense of the integral against the FBM? Do you find enough time regularity of the solution, or what?
No, sorry, yeah, this is something I also hid under the carpet. So yeah, like as Avi correctly points out here, there is a W dot, and actually W is not a process which is differentiable in time in a classical sense. So this term actually is not naively well defined. So no, what we do is simply the standard Galilean transformation which reabsorb it. So essentially, if you just, instead of U, you define U tilde, which is by keeping track of how much translation you do by WT in the space variable. Basically, this equation is formally equivalent to another equation where this guy is not there anymore, and B has been shifted along W. So we just use that maneuver. I mean, what we define solutions to this equation as the objects you obtain after this transformation from solutions to the other equation, which is now perfectly well-defined random PDE, and we do establish existence and uniqueness for that equation, effectively.
So this only works because your noise is homogeneous in the space variable?
Yes, correct.
Yeah.
I mean, if it's multiplicative noise, I think you can still perform at least formal flow transformation, but it's nicer to pull it off. It's not so obvious.
Do you need some information on the Jacobian, right?
Yes, I think Catelier and I don't know, Rebeillac is the other author. I think maybe they accomplish something like this. They do use a flow transformation to deal with SDs with multiplicative noise, but I don't know in detail.
Great. I suggest really we will have the discussion also at the end. Thanks again. I ask to unshare, and we move to Lukas Anzeletti of Université Paris-Saclay, who will speak about regularization by noise for SDEs with fractional Brownian noise and the comparison of different notions of solutions. Lukas, the floor is yours, please.
Okay, thanks a lot for the introduction, and also thanks for the invitation to speak. Okay, so I will talk about regularization by noise for SDs with fractional Brownian noise, and then depending on how much time I have left, I will do a bit of a comparison of different notions of solutions. So Lucio already mentioned like a very nice global picture of what's going on, and I will try to focus on a bit of a maybe niche result just on weak existence of solutions. We also have results using stochastic Sewing lemma on uniqueness and strong existence, but I think in 20 minutes it's nicer to do the other result. And most of what I'm talking about is based on joint work with my two advisors, Alexandre Richat and Etienne Tollet. Okay, so throughout the talk, our noise will be a fractional Brownian motion with first parameter h smaller equal than 1/2, where we saw already that the case of h equals 1/2 denotes a Brownian motion. And as Lucio mentioned, this has the drawback of not being Markov when h is not equals to 1/2, and it does not have a martingale structure, but it's for the smaller h's, the rougher it gets. And this gives us more regularization, as we will see later on. And first, a few benchmark results. So it's been known for a few decades now that the reflected Brownian motion solves the following SDE, where L denotes the local time of the solution X. And okay, we will also define this later on, but intuitively, we characterize this as the integral from 0 to t of a Dirac in 0 XR dr. So what this is telling us is that every time we hit 0, we get a contribution from this Dirac that puts the Brownian motion above 0 again. And this equation has a strong solution, which is the reflected Brownian motion. And now we could ask ourselves, okay, if we don't put a Brownian motion, but a fractional Brownian motion with h smaller than 1/2, our intuition is telling us that somehow we should get more regularizations, so we should also be able to cover such distributions. Or if phi has some singularity, if it's some other finite measure, or if it's in some more general class of distributions. And okay, let me just mention these two like benchmark results. The classical ones by Nuela and Oknin, they cover some singular functions in the fractional Brownian case, and in the case of Brownian motion, Krylov and Röckner give like an LQLP condition on the drift phi. And what our approach to this kind of equation is the following. First, we rewrite the equation by x tilde is equal to x minus b. And then we arrive at such an equation. And now we know that usually for ODEs, we need some kind of Lipschitz condition on the right-hand side or continuity condition to either get uniqueness or, in case of continuity, existence of solutions. So we kind of want to mimic this behavior. And we look at the right-hand side of our equation, and we look at the map x maps to what we call the averaging operator of the fractional Brownian motion applied to phi, which is now a process in both time and space. And we hope that this has some regularizing effect in space so that we will have enough regularity to get existence and or uniqueness to this equation. So let's get some intuition about this averaging operator. So first, let's just take some bounded measurable phi, then everything here is well defined. And to get the real intuition of what's happening, I choose the function phi is equal to the indicator function on some interval. So what our averaging operator is doing now, W is just some path. You just imagine some Brownian path or some fractional Brownian path. It's just measuring how much time we spend inside this integral up to time t. So we can either look at this process as a process in time or in space as soon as we fix the other variable. So first, let's fix the space variable equal to 0. So we start our process in 0. And we see that, okay, every time we're inside this box, which represents this region where the indicator function lives, we get a contribution of our averaging operator of the process corresponding to the averaging operator here. And every time we're away from 0, we're away from this box, we just stay constant. So in particular, this green process that we obtain as soon as we fix x equals to 0 is monotone in time, and we will make use of this later on. And on the right-hand side, what we see is we fix t equals to 1, and as soon as we turn our heads like 90 degrees to the right, what we see here is we start at different initial values x. We look at the process x plus w, and we see how much time we spend inside this integral. So if we start somewhere in the very middle of the interval, we will spend a lot of time inside. The further we get away, the less time we will spend inside here. And now note that, okay, we started with a bounded measurable function with this indicator function. And what we obtain now is something that looks kind of smooth in as a function of space. So what we hope is that this will have some Lipschitz behavior, but we can see at least that this is continuous. And what was crucial here is that our blue path is really rough, which is kind of blurring out the starting point because we immediately move away from the starting point. Imagine that the blue path would just be a constant. Then what we would see on the right-hand side here is just if we start inside this box here, that we spend the whole time inside this box, and if we start outside, we spend 0 time inside this box. So we would get something that is highly discontinuous. Okay. And another notion that we need, and then I think almost done with definitions, is the definition of a local time. So heuristically, we already saw that we can define the local time as the integral of a Dirac. So what we could do in case of Brownian motion is we just look how much time does the process spend in the neighborhood of the point we're interested in, and then we scale by the length of the neighborhood. And another property that this local time fulfills is the so-called occupation time formula. And okay, this is more or less completely intuitive, because on the left-hand side, what we see for some, let's say, interval A is, okay, we take an indicator function A, we look at WR, so we see how much time does WR spend inside this interval up to time t. On the right-hand side, what we see is, well, this local time should tell us how much time we spent at point X, then we integrate over A, so it's again telling us how much time we spent in this interval A. And this, by the usual measure theoretical arguments, carries over to bounded measurable functions F. Okay, a quick picture. So in red, we see the local time at 0, and in blue, we see a Brownian motion. And we see that every time we hit 0, we get a positive contribution. And every time we're away from 0, our local time just stays constant. So again, the local time here is monotone in time as soon as we fix the space coordinate. So this reminds us already of the averaging operator we saw before, and we will make a clear connection between the two of them later on. Okay, so we care about this equation, but how do we actually define a solution to this equation? Well, we have the two kinds of classical solutions. Without going into detail, what both of them should be doing is they should solve the equation, first of all, and second of all, they should be defined on some filtered probability space that works nice with the fractional Brownian motion, such that they are adapted with respect to the filtration that is defined on this probability space here. So it kind of is telling us that the solution should not look into the future, but it should really be adapted to some filtration that makes sense with the fractional Brownian motion. But here, what we can also define is something called a path-by-path solution. And the reason why we can do this is the following. If you look at the equation, we can really just plug in any omega we want, and we get a completely deterministic equation, and everything's well defined. Because we have no E2 integral or something like this here, we can really just plug in omega, and we get the fractional Brownian motion of omega evaluated at time t here. So what we call a path-by-path solution is a map from omega to the space of continuous functions, such that on a set of full measure, x of omega just fulfills the equation that is then deterministic. Okay, the first implication here is classical, that strong existence implies weak existence of solutions, and weak existence implies path-by-path existence, because every weak solution in particular is giving us a solution to this equation for almost every omega. It just has the additional property of being adapted with respect to the filtration. So path-by-path solutions are like the weakest kinds of solutions compared to the other ones. Okay, as we heard a few times already today, the idea of regularization by noise is that rougher noise is giving us more regularization. And also, apparently in every talk about regularization by noise, this result has to be mentioned by Catelli and Gubinelli in 2016. And what they are doing is they can say that there exists a unique path-by-path solution to the following equation under the restriction that alpha is greater than 1 minus 1 over 2h. So this was already mentioned by Lucio, so I think I don't have to spend a lot of time here. Let me just mention that, as we saw on the first slide, we are very interested in the case of phi being a Dirac. And in this case, after doing small computations with the alpha, we see that this result gives us a unique solution for h smaller than 1 over 4. And our main objective at the beginning was to either establish sharpness of this inequality or to extend it to larger values of h. Okay, so as I said at the beginning, you can either do this with stochastic Suing or with an approach via nonlinear Young integration, and I will present this now. So we look again at our equation of interest. We rewrite it again in the following way. Then we just introduce a small notation For f defined on 0t, we define by fst, we let this be ft minus fs, so just the increment. Okay, let phi still be a nice continuous bounded function, and we consider our averaging operator again. And we look at the right-hand side of our equation. Then what we can do is, after minor manipulations using the continuity, we can rewrite this right-hand side of the equation as such a limit of what looks to be more or less a Riemann sum. And I think it's very believable that if we have sufficient regularity here, that this will converge to something, and this something we will later call a nonlinear Young integral. Okay, so in the case of having a continuous bounded function, we could like rewrite our right-hand side of the equation as such a nonlinear Young integral equation. So far, we have gained more or less nothing, but now we want to consider the case where we don't just have a bounded continuous function, but we somehow want to go over to distributions. So in the case of bounded continuous functions, one can use the occupation time formula and rewrite the averaging operator as a convolution of the drift with the local time of the fractional Brownian motion. Okay, and now usually we know that if we have a convolution and two functions have a certain regularity, this regularity will more or less add up. So in this case, if the local time is very regular, then we can choose phi to have very little regularity and even to be a distribution. And still the convolution will be well defined and will be a function itself with a certain amount of regularity. And to rigorously do this, you have to, or you can work in Bezov spaces to get the best results possible. And then if the local time is sufficiently regular, you look at the drift phi in some Bezov space and you do the convolution as this dual bracket here. So you can extend the definition of the averaging operator via the local time to distributional phis. As soon as we did this, now we know how we can define a solution to our equation, not just for nice phi, but also for distributional phi. Because what we can say is we call x a path-by-path solution to our equation if x tilde equals to x minus b fulfills the nonlinear Young equation corresponding to our equation for almost every realization of the fractional Brownian motion. In order for this to be fulfilled, we in particular need the right-hand side to be well defined. So we need a certain amount of regularity both on the averaging operator and on x tilde. Okay, so now that we know what a solution even is, I want to sketch the proof of how we actually get the solution to the equation. So first of all, as we consider this equation now, this nonlinear Young integral equation, we have to determine the regularity of the averaging operator because we need enough regularity such that the right-hand side will even be well defined. And this can be done using the regularity of the local time of a fractional Brownian motion. Okay, we did not do anything huge here. We just obtained the result that was most fitted to the drifts we're interested in. You can also have a look into Hagen and Butkovsky for similar estimates about the local time of a fractional Brownian motion. Okay, and now we know the regularity of the averaging operator here, but also it's relevant what the regularity of x tilde is. And a priori, we don't know a lot about the regularity of a solution to such an equation. But what we know for sure is that it will be monotone in case that our drift is non-negative. Because if our drift is non-negative, this averaging operator applied to phi is defined as a convolution with the local time. We saw at the beginning that the local time is monotone. So if we take the convolution with a positive function or distribution, this will still have monotone behavior. So we integrate this, so x tilde will be monotone in time. So it might be very rough in terms of Herder regularity, but it has finite one variation. So in the p-variation sense, it is the smoothest we can hope for. So there has been a lot of investigation or a lot, but in recent years on nonlinear Young integrals in Hölder regularity. But in our case, it is more fitted to have it in p-variation. So we just formulated nonlinear Young integral equations in p-variation that allows us to make use of this finite one variation of x tilde, because this is very smooth then, so we can assume less regularity on the averaging operator applied to phi, so we can allow for worse phis. By the way, also, if someone is interested in nonlinear Young integral equations, there is a very nice review by Lucio that I didn't cite here. So as soon as we know this, we can search for x tilde in the space of functions with finite one variation, because we know it has to lie inside there. We can do this via an Euler scheme, and as soon as we have this, we're done. Just a small side remark. Okay, everything here looks very deterministic in what I did. So just to mention that, yes, really, this requires no probability theory, but this is only the case because all of the probability theory is hidden inside the regularity of the local time, because it is very hard to cook up a deterministic function that has a local time, and even more so that has a regular local time. Okay, so I kind of did the proof before the theorem, but I will now state the theorem that is not in the most general form, but as I started with the Dirac, I will just formulate the theorem in case of having a non-negative finite measure. In the actual theorem, you can play a bit around with the Bezoff parameters. But in case of having a non-negative finite measure and h smaller than square root of 2 minus 1, we can show with the procedure I showed on the last slide that there exists a path-by-path solution to our equation. And afterwards, building on this construction, we can also show that we can actually make this equation adapted, so we can construct a weak solution. And as a corollary of the general theorem, not the one written here, the one where you can play a bit around with the parameters, if you set h equals to 1/2, you even get a weak existence to an equation like this here, where xi is just cutting off the function somewhere. So it's just a non-negative bump function. But you have a singularity at 0 that is, for example, not covered by the Krylov-Röckner regime. But here we really just get an existence result and no uniqueness. Okay, I don't know if I have a few minutes left. Otherwise, I will close the talk.
Make it here 1 to 3 minutes, please.
Okay, 1 to 3. I will.
Yeah.
Okay. Then let me just mention the following, as it is a bit related to what I talked about throughout the talk. But here I just take a Brownian motion. I look at the following equation here, and okay, in the talk, like everything, we constructed a weak solution, but this was rather something that we did on top after constructing a path-by-path solution. Everything before was really based on like a path-by-path argument. And just to give you a brief picture, as mentioned earlier, there is this result by Krylov-Röckner where you can allow for some singularity in both time and space. And there still exists a pathwise unique and therefore also a strong solution to our equation. But in the path-by-path sense, you can only get uniqueness for a bounded measurable function. And uniqueness in the path-by-path sense means that you fix some omega, you throw in the omega, then you have a deterministic equation, and you want uniqueness to this deterministic equation for almost every omega. So at least my hope is that one can use similar techniques, at least for non-negative drift phis, and maybe make use of this p-variation framework of nonlinear Young integrals in order to also get some uniqueness results here, because you more or less have the path-by-path setting for free. And there are a few counterexamples on path-by-path and weak solutions, but the whole picture is still very unclear, I would say. And it's maybe also an interesting question to extend this result by Davy to some to some drifts of this form as in Krylov and Röckner. Okay, I will end my talk here, and thanks a lot for the attention. Looking forward to questions.
Great. Thanks a lot. I suggest that also due to time reasons, there will be discussion at the end. We move to the fourth presentation, and we will have surely a lot of questions later. So our final presentation is by Igor Honoré of Université Claude Bernard Lyon 1, who will speak about selection by vanishing viscosity for the transport equation. Thanks. Thank you also, Lukas, again.
Thanks.
Is it okay? Hello, thank you for the invitation. So I'm assistant professor in Institut Camille Jordan in Lyon, and I'm very glad to present you my one of my very new results. The topic will be about vanishing viscosity solution for transport equation. It's the counterpart, the deterministic counterpart of the zero noise limit for stochastic differential equation. First, I give you some examples.
Igor, I think we do not see the slides. Yeah. At least I do not see them.
Okay. Strange. Is it good now?
Yes, maybe to the full screen. Just put it to the full. Yeah, but we see the slides. Great.
Okay.
This is the
sorry for the mistake. Okay.
Great.
So you didn't miss anything important. First of all, I will present some example of regulation by noise and what can we expect for the transport equation. And after that, I will explain what do I mean by vanishing viscosity solution, and I give you one result, and after I give you a glance of the idea of the proof, and if I have time left, I give you an application to the non-viscous Berger equation. So let us consider the following SDE. The diffusion coefficient nu is called here viscosity, which is inspired to the fluid mechanics. And what we expect, like in the previous speeches, we expect B to be very rough. And there is naturally the PDE, the parabolic PDE, which is very linked to the SDE through the Feynman-Kac representation, for example, and which is a very powerful tool, because you can consider very rough drift B, and you can regularize it, and you still get the Feynman-Kac representation, and it gives you, for free, a uniform control of U. For free, I mean by that, it doesn't depend on B, on a regularized B, so you can, if you want, go to the limit with the regularization parameter, which is not available for function because it's not uniformly continuous, but still it's true for real. You can use the Bolzano-Weierstrass theorem. It's not enough, of course, for the analysis of transport equation, but still it's quite interesting tool, I think so. Below, I just present you something very important for me, which is a deterministic counterpart of the regularization by noise in this Brownian case. If you consider the PDE and the source function is gamma Holder's continuous, then the solution is 2 plus gamma Holder continuous in space. It's the so-called parabolic bootstrap from the Brownian term in the SDE or from the Laplacian in the PDE. There is a gain of +2 of regularity for the solution. If you consider something else like an alpha stable process, the gain will be alpha instead of 2. Another aspect of regularization by noise, if you consider a problem which is typically not regular enough, and this lack of regularity yield a nil-posedness, nil-posed problem, and if you add a noise, you can expect the problem to be well posed. what I focus on, it's on the transport equation. Usually, if you focus on the Lipschitz case, the problem is well posed. You can use, for example, a characteristic method, and there is absolutely no problem. If you are out of this Lipschitz framework, it's quite hard. I can mention the seminal paper by Dipernal, Lyons, and Ambrosio. If B lies in a suitable Bezoar space or is bounded with bounded variations, and the divergence of B lies in the suitable bounded space, then the problem is well posed. But for a pointwise regularity fewer than Lipschitz, typically if B is Holder continuous, it is well known that the problem is not well posed anymore. There is a famous counterexample here. But if you add, like written in front of the slide, you have a noise, you can expect some well posedness. It was done, as previously mentioned, by Flandoli, Gubinelli, and Priola, when they add a noise, here a multiplicative noise with a Stratonovich symbol, and they establish, still with conditions divergence of B, the well posedness of this partial differential equation. Okay, so what's happen if there is no more noise, or if any modifying parameters goes to infinity to go to the transport equation target? When there is no more noise, when the viscosity goes to 0, I call this vanishing viscous solution. I will be go in more details later. For all of my knowledge, all the results that I saw are negative about uniqueness. I mean, Atanasio and Flandoli in 2009. They tried to get the zero noise limit with the previous counterexample and the SPDE, and they get not uniqueness. At the limit, there are two different solutions of the transport equation. And if you don't look at regularization by noise, but just regularization by, I don't know, by convolution with a smooth kernel, still there is no possibility to get uniqueness, which can be seen in a more recent paper. So the next question can be, what about existence? What can we say about existence if you consider the rough coefficient B? Before to give my result, I just need to introduce what do I mean by vanishing viscosity. To do that, let us consider the Kolmogorov equation or the parabolic equation. Sorry for that, it's not a lot of probabilistic terms here. I just put a minus here because it's more like a PDE point of view. If you want to put a plus, you have to make a tiny change. You consider so the parabolic equation, and you regularize the bad guys. Can be a distribution, the coefficient B. You regularize it, and this problem, this Cauchy problem, is well posed. There's absolutely no problem. You can see it in Friedman. There's absolutely no problem because of regularization of B. There is pointwise control of B. Be careful, they blow up with M. And here is the true regularity of B, which lies in a negative regularity in Bezoar space. First, the weakest solution that I consider. First of all, I consider naturally that the modified coefficient converges towards the true coefficients in the suitable Bezoar space with a loss of regularity, loss of epsilon in terms of regularity. And the only thing that I ask for the solution U M nu before passing to the limit on nu and M is to solve the parabolic equation. And after some computation, I will show that U and nu is order continuous uniformly in M and nu. And I will go to the limit thanks to Anzeletti theorem. Then I have to consider the result for a given T and in all subset of K, compact subset K of RD. Now, if we want to consider a more usual solution, we can integrate the transport equation again, a smooth solution phi. And if we can go to the limit in some sense of the previous solution, the previous mild vanishing solution, then we can consider the usual weak solution. So here my my first main result. Let us consider gamma between 0 and 1 strictly. The case gamma equal to 1 seems to be not true with the method. I will explain why, where is the blocking point. If beta lives in R, I don't know, consider beta equal to 0, which is not a real constraint. It's just to make the previous control of BM easier. If you want to consider this case, you can imagine B to lie in the L infinity space. There is absolutely not a problem. F and J, the sources function, are gamma order continuous. And we show that for a given constant, which depends on the parameters of the problem, if nu is negligible in front of exponential of minus this constant m exponent 1 plus beta, then we get this quite sharp control of the solution, but in terms of mild vanishing viscous solution. I don't pretend that the coefficient u, bm, and nabla u m nu converge pointwisely to the b nabla u. I just say that before passing to the limit, u is solution of the parabolic equation. If there is more constraint on B, sorry, for example, if B is division free and if beta is fewer than gamma, that means that B has to be more regular than minus gamma, still with negative regularity, then we can get a weak solution. Now, if B is not division free, then I obtain for positive regularity, I mean that B has to be orders continuous with a positive index, then the solution is a weak solution, and I get a control of the regularity of the time derivative. So a first consequence, almost direct, of this result is that if we integrate in time the parabolic equation and go to the limit with this constraint, then because the second order part term, I mean the Laplacian, is in front of the nu, which go very fast to 0. In the paper, I call this this phenomenon, maybe I call this phenomenon, sorry, regularity by turbulence, because in fluid mechanics, turbulence, one of the aspects of turbulence is when there is a Reynolds number going to infinity, which corresponds to the case of vanishing viscosity. And if we take the time integral of the parabolic equation and go to the limit, then the right-hand side is it's all function living in a gamma order function. Then we obtain, thanks to a kind of averaging in space, in time, sorry, technique, we obtain a new regularity because we can imagine B to be as rough as we want, and nabla U lives in a negative Weber space because U is gamma order, so the derivative of U lives in a negative regularity space. So the counterpart of this new, to the better of my knowledge, new result is that I don't get any uniqueness of this result. That doesn't match, actually, that go beyond the Bonny theory about paraproduct. If we look at the incompressible case, the case where B is divergent-free, then we can, through the weak formulation of the PDE, get a distribution meaning of the product. The product in the sense that we look at the limit of the regularized and the solution of the parabolic equation. And now, if we look at the positive continuity, I mean, if B is Holder continuous, then we match the Bonny's paraproduct condition. Beta has to be beta or alpha here, the opposite of beta has to be greater than 1 minus gamma, like in the Bonny theory. But still, if we again take the term averaging, we, thanks to this equation, we still have a +1 gain of regularity. Maybe it's cheating because we integrate in time, so we gain a regularity, but still, I think it's quite interesting. So I still have time. I give you the main ideas, I think, to prove this result. The idea is to approximate the parabolic equation as sharp as possible. To do so, I consider the flow associated with the regularized drift, I mean the regularized B, coefficient B, and I rewrite the parabolic PDEs, where the left-hand side is quite nice because this coefficient is constant in space. So the fundamental solution of the differential operator on the left-hand side is Gaussian. We can control it, and the left-hand side, B delta, corresponds to the error term. Actually, we will see that it's a remainder term. Thanks to this formula, I can write a Duhamel formula with the corresponding fundamental law of the left-hand side, where it's a Gaussian term, which looks like actually each kernel, and there is a perturbative term depending on B and on the flow. The flow exists and is unique by Cauchy because B is modified. I didn't precise that. And by definitions, we can see that the density matches when when psi and tau matches with x and t. I didn't precise for the flow. Sorry. Something very important, that tau and psi correspond to two parameters, two freezing parameters, and they have to be tailored later to be as sharp as possible in the controls. And something important also, that the solution U and nu does not matter on do not depend on t, tau and psi, because the PDE, the initial PDE, does not. And just here some usual computation about each kernel. You differentiate the kernel, then you obtain a singularity in time, and also in the viscosity term. Our goal is to have a positive viscosity contribution to be able to go to the limit when nu goes to 0, and the other term, multiplicative term, will be negligible if nu goes to 0 very quickly. One method to smoothen the viscosity is to put what is on the exponential term. It's a quite classic inequality. So, like I said before, the main part of the proof is to control the order norm of the solution. To do that, we can write this inequality by triangular inequality and by the previous Duhamel formula. The psi prime corresponds to another point, x prime. And the two first terms are not so difficult. They are the two main terms. And the last terms is obviously the remainder term. So the most nasty term. And to do that, to control the last term, I will proceed as usual when you have to prove some parabolic bootstrap. For example, if you get the IT equation and you have to show that the solution have a regularity gain of +2, you have to you can consider two different regimes, the diagonal regime where the two considered points, x and x prime, are quite far away from each other, and the off-diagonal regime, they are close together, and the off-diagonal regime, they are far away. Usually, for the parabolic bootstrap, alpha 1 and alpha 2 here, which are two parameters that we have to calibrate again a little bit later, usually they are equal to 1/2. That works if you want to have a gain of regularity of the solution, but that doesn't work if you want to use the vanishing viscosity to overwhelm the potential blowing up on M. So when you consider this constraint, you can see there is a time. We can call it a cut locus time, because in the first regime, because 2 points I closes, I just take the same parameter for the 2 points, x and x prime, and when they are far away, I consider two different parameters, psi, sorry, being equal to x and psi prime being equal to x prime. We can see this like a cut locus strategy because in a Riemannian manifold, sometimes you can see that there is a geodesic which are branched on the same point, and it's a kind of analogy. After some quite easy or not computation, it depends on the opinion, I see naturally that alpha 2 and alpha 1 have to be equal to that. And after this choice, I see that the remainder term goes to 0 when you go to 0 very quickly, exponentially quickly in terms of M. And of course, it's not for free when you change.
Igor, I'll just ask you 1 or 2 minutes, say 2 minutes max, and then finish, please. Just
2 minutes?
due to time,
Okay.
yeah, 2, 3. Thanks.
Okay, it's almost finished. 2 minutes. Okay. So I conclude after dealing with additional terms by the so-called Anzeletti theorem, and there is no condition at all on B. But to get other solution, weak solution, I use some Bezoff duality, and I have to consider some condition on B. The lack of my results, I don't get any uniqueness because there is no polynomial condition on U, and I can't to get any balance between U and M to obtain any uniqueness. As I said, there is no condition on the regularity of B. So I can match B with U in the consider transport equation, which is exactly the non-viscous Buckers equation, and I obtain the same result, except that here the condition to get a weak solution is gamma strictly greater than 1/2. I don't have a precise explanation of that, except under this regularity there is some pathological behavior of the solution. I know that there is some problem about this equation with when you use the characteristic method or eventually other method. There is a time where the solution can have can have discontinuity, and maybe this this solution of viscosity avoid this time of discontinuity, because the choice of subsequence can depend on the current time. And the idea of the proof is just a fixed point argument, and when you change the norm of B by the norm of U, which is given by the Helena representation. And thank you for your attention, and here are some bibliography.
Thanks a lot. Apologies for interruption, but yeah, just to be on time. Also, again, due to time reasons, I suggest we go now to the discussion of Oleg, and all the questions from the participants, I suggest, are put following the discussion. Thanks. Oleg, please.
Right, so I'm not sure what is the format, but so
Igor,
let me just
Igor, just could you unshare, please? I think this is, yes.
Right,
Great.
so I have I wrote some questions here for all the participants, so maybe let me just ask a couple of questions to each of them, and then yeah, I'm not sure what is the format. Okay, so maybe let's start with Helena. So could you please maybe share your slides?
Yes.
And while sharing, I'll ask my question. So in some previous versions of this talk, or maybe I'm wrong,
yeah,
I think the main application was that you would like to apply what you did then to do the Brooks diffusions for Levy, driven by Levy noise.
Yeah.
And my question would be, so if I understand correctly, so somehow this provides like a very general setup. So in particular, as the driver V, there is no need to take the derivative of a Brownian motion, but you can also take the derivative of, I don't know, some fractional Brownian noise or any other noise. So my question would be whether this is correct or not.
Mm-hmm.
And then the second question would be, so we know from, for example, the work of Hoa, that in the Brownian case, the Brooks diffusion is strongly unique, is strongly well defined. So do you expect that here it will be only defined in the weak sense, or you think that in the case of the Brooks diffusion for Levy, one would also be able to get a strong solution? So this is what I want.
Okay, yeah. So actually, this Brooks diffusion is an application already from the martingale theory. So it's not the, you would not need like a weak solution or something.
Mm-hmm.
It's already like an application of this martingale solution problem stuff. So you could basically take everything which fits into this rough regime. And one-dimensional example would be this Brooks diffusion. You could also take the derivative of some Brownian sheet, which will have the same regularity then, so -1/2 which also fits into the rough case. But in general, we only get like weak solutions here. So there's there would be no strong solution in our case. So you said that Core has some work where you have for the one-dimensional Brownian motion strong solutions?
Exactly, yeah. So I mean, Ho is with us, will correct me if I'm wrong, but there is a work of Ho, Leonid Mitnick, and Hu, where they did, when the noise is a Brownian motion, the drift is a derivative of another Brownian motion, and then they show strong. Well-posedness. And my question would be, would you expect something similar here, or would you expect that because of the Levy noise, I don't know, strong will not hold? What do you think? Or so is it like a problem with the method, or it's like some fundamental fact which is wrong for the Levy case? What do you think?
So first of all, this theory will only give you weak, and if you lower the alpha, the regularization is less strong, right? So it could be that the strong solution breaks down then.
Mm-hmm.
What is also interesting that actually if you can get weak solutions probably in the whole subcritical regime. So in fact, you can construct this enhanced version of this white noise down to the critical case. So critical would be beta equal to 1 minus alpha, which is equal, which is when beta is -1/2 minus alpha equal to 3/2. So in that case, you can construct this enhancement, and there's this gap. So yeah. But this is nothing for strong or something. This is just that you would probably get down to weak existence.
Okay,
but
thank you.
Yeah,
then,
you will not get strong for the Brooks diffusion out of that work.
Right, and then also you mentioned there are 2 Ito formulas in the very end. I didn't quite get what
Yes.
was the difference between one and then you said you proved another. What is the difference?
There were 2 Ito formulas.
Yeah, so one you said one was in the very end and one was almost in the end.
So that one was probably the one in the end.
Yeah, so there is this one, and then there was one on slide 15 or 14.
Okay.
Before
that one.
This one, yeah. What is the difference?
So yeah, the difference is for smooth enough function. So this UN, you get the usual one. So this integral will agree for smooth enough integrand with the dz integral, of course. And also this guy will not be a distribution if you mollify the UN. And how you prove this extended Ito formula is by mollifying the UN. Then you get the usual one. And if you go to the limit, you have by stability that these integrals will converge to that rough integral. And this guy you need to assume because it's a distribution. Yeah.
Okay. Thanks.
So this is basically, this is the limit of that one. Exactly.
Okay, very good. So Andrei, what we're doing now, question from people, or I go to next participant?
I suggest we just move to other participant,
Okay, so then thank you very much. Yes, thanks Helena for the great talk. So
thanks for the
now
question.
I have some questions to Lucio. So first, I would start with some things. So you've showed us in the very end this bound that was crucial for you, but I don't understand why then it was important that Q was less than 2. So in the very end, you had some bound.
Yes. So yeah, that's part of the mathematical artifact. So essentially, whenever you use stochastic skewing, you do need that. So you have this fundamental germ you used at the beginning, and you always do need that. This germ basically is, let's say, I mean, you need 2 estimates essentially, one on A and one on delta A. For A, you need an estimate where you have a control with an exponent greater than 1/2, and then for delta A, you need the exponent greater than 1. So the key point here, and this is the skewing itself, I mean, is not something related to the SD, just to the tool we are using. So this guy here, the only information I have is that it's strictly greater than H, which actually, when I take one derivative more, I'm gonna be very vague here. Roughly speaking, this term becomes almost 0. And application of skewing forces me to have this term here creating the exponent greater than 1/2, which roughly speaking forces Q less or equal than 2.
So this formula is valid not for all Q. So this formula is valid only for Q less than 2.
No. I mean, I'm telling you the results you obtain are then based on the application, and that's where we need the assumption. This formula itself, when you take alpha greater than 0, is true for any Q. When you take alpha smaller than 0, I think there is some condition on Q, but it's not just Q between 1 and 2. It's something a bit more refined, if I remember correctly. I will need to check out the paper again.
Yeah, okay, thank you. Then I have like a more conceptual question. So could you please go to the slide when you talk about pass-by-pass solutions?
I mean, okay, because I mean,
yeah,
this
somewhere
one,
here.
Okay.
Yeah, exactly. So, okay, so alpha can be negative here, right?
Yes.
So how would you understand pass-by-pass? Is it in the same sense as in Lukas talk, or you have a different definition of pass-by-pass solution? Because then then B would be just a distribution, so then it is not clear how you would define it in a pass-by-pass meaning. Is it the same as Lukas or different?
Yes, it's the same as Lukas. You can still interpret the pathwise SDE or random ODE if you want as a nonlinear Young equation. And then you can show path-by-path uniqueness among all possible solutions to the nonlinear Young equation. Yeah, I'm sorry, I skipped details because I mean there is way too much things to say in 20 minutes. But yes, it's the same.
Okay. And is your techniques so here you use like only if it's pass by pass, so you use here only deterministic queuing, or how come?
No, here we actually use
by pass. How it is possible?
We actually use the technique developed by Shaposhnikov. I mean, essentially, okay. When you have the regularity of the average field in this framework, it only gives you existence, but at least it allows you for the SSD to be meaningful. And then there is this class of results which actually go back to Van Kampen in the ODE case, which effectively tell you if you have a sufficiently regular flow for an ODE, then solutions are unique. I mean, even if the drift were not Lipschitz. If you can show me a globally well-defined flow, then automatically uniqueness of solutions will follow. And that's what we employ here. So actually, I mean, so we first prove point B, and then from this path-by-path uniqueness follows.
Right. And to prove B, you do stochastic queuing. Yes.
And we run Kunita's argument. Basically, you need to use estimates of this form and several other things. I mean, you first show strong existence and uniqueness, then you derive bounds for which do show at least the existence of other continuous flows by Kolmogorov criteria, and then you start announcing more and more, basically.
Okay, I see. So somehow, okay, I see. Very good. And then my last question would be about your PDEs. This is what Avi asked, but I'm still a little bit puzzled. So is it possible to just define a solution of this PDE, like, in a usual way when you, I don't know, approximate, when you either have some, try it with the test function or approximate your noise by something, or I don't know, whatever concept, but without, but somehow more directly, or what is the story here?
Okay, if you modify the drift and push the modification to 0, this is exactly concise with what we obtained here. And that's again because you're just using the representation through characteristic lines and the fact that the associated flows converge to each other thanks to the stability estimate. If instead you regularize the noise, but you fix B irregular, potentially you lose everything. Because I mean, if you regularize the noise, you lose the regularizing effect, and you end up with an equation which is ill-posed potentially.
Right.
So in that sense, I would not know how to put the modification on the noise. Then, I mean, without doing the Galilean transformation freak, I mean, it's very handy to use it. But for instance, already Catelier in 2016, he did justify this kind of equations in a more classical rough path manner, at least for h greater than 1/4, say. Because I mean, you need to work with rough paths. So I mean, you can actually sort of come up with a definition of control solutions for these kind of equations, and then actually show that you can interpret these guys as rough integrals in a sufficiently weak way, like testing against smooth functions.
Okay, and then so then these concepts coincide. Okay, very good. So maybe thank you very much. Let's now move to.
Thanks for the questions.
Yeah, but thanks for the talk. Let's move to Lukas. Right. Let's see. Yeah, so basically, so my question to Lukas would be, so basically, if I understood the first part of your talk correctly, so the point is that once, so you have any equation, it can be driven by anything. You don't use Gaussianity. The only thing you use is that the local time belong to a certain class. And if once the local time of the drift belongs to a certain class, then you deduce existence. Am I correct?
Yeah, okay, so this is rather the answer than the question, right? Yeah, you're correct. The only thing that's happening is maybe when, like we show this path-by-path solution, and then for a weak solution, we need some estimates, like to get like some tightness, we need some estimates on the local time again, but this is, okay, I don't know for which processes you have this, but if you have this for whatever process you want, then it's also,
I see. So
we need to estimate like the moments of the increments of the local time, and then then we get the adaptiveness.
Right, and so if I also understood correctly, so contrary to what we discussed 5 minutes ago with Lucio, so you do it directly, so you don't use any flows, like there is no kind of stochasticity involved once local time is given somehow. Is it correct?
Yeah, in this approach, yes, but I think I'm not sure, but here we then get no uniqueness result with this nonlinear Young technique. Like to get uniqueness, we have to use stochastic swing.
And how would you then, okay, so then you have some pass by pass solution for each omega. So how then you would show that it is indeed weak, that everything is indeed adapted in a nice way and so on? How is this done?
Yeah, I mean, since we don't have uniqueness, we can't show that like any path by path solution is adapted, but the particular, we more or less run through the same Euler scheme we do in the deterministic setting. And then controlling the increments, we use that we have nice control of the moments of the local time, because the increments will more or less be the increments of local time because it's the averaging operator and we define it in this way. And then we get tightness and we can pass to the limit and the filtration will still be okay. But we don't get a strong solution because we don't have any uniqueness result.
Okay. And also maybe because it was very sad that you didn't have time, maybe you could say maybe 1 minute about your fantastic results about these pass by pass solutions versus like that there are SDs where they have pass by pass, but not about this thing.
Yeah, I'm not sure if it's fantastic, but so Bresch and Shaposhnikov did this in the two-dimensional setting, that they more or less construct. So what I just generalized this to one dimension as this relies on 2 dimensions. And the idea of what I did at least is I used SDs that are well known, like Bessel bridges, Bessel SD, and you patch them together in a way that forces your solution to look into the future. Like you more or less, you want like solutions on the whole interval. And the way, if your solution is just going whatever path it's going, without looking into the future, it will arrive at a point where it can't go any further. But if it kind of anticipates what will happen in the future with the Brownian driving noise, it will before choose the right track in order to always be able to continue on the whole interval. So it kind of has to anticipate what the Brownian motion is doing in the future. But it's somehow a bit, I mean, what is a bit artificial, I don't know how to say, is that you really need like solutions you consider solutions that have to be defined on 0t and not up to some stopping time or whatever. So you really have to be defined on the whole interval in order to construct such a counterexample. I don't think there exists like a local counterexample.
No, but that's still very interesting. So somehow, your last column tells that it's possible that everything is all right. You have pass-wise, but not pass by pass. And then your like penultimate column tells that it is possible that there are interesting cases when there is even no weak existence, right? So
so I would say this, where it says weird phi is easier, that you have no weak solution, but you have as many path by path solutions as you want. And then a bit harder, but in a similar spirit, you can construct like one weak solution, but as many path by path solutions as you want.
Okay, and then you said that they all so the idea would be to take phi to be 1 over x or something like in this direction, right?
Yeah, and phi will be like, phi depends on time here too. Otherwise, I don't know how to make it work. So phi will be differently defined on different intervals.
Okay.
It's also an archive if you're interested.
Yeah. Okay, thank you. And finally, I have a couple of questions to Igor.
Thanks for the question.
Yeah, thank you. So Igor, also thank you. And Lukas, thank you also for presentation. Igor, also thank you for the presentation. So I'm a bit confused. Could you go back to like where you just first started with non-uniqueness stuff? Yes, here.
What do you mean?
No, above slide 6. Right.
Okay.
So what is the story here? So these people, Flandol and Anastasio, they took some drift and then they showed that if you take out the noise, then you will converge okay, somewhere. Okay, so what is why we should be happy with this thing? Okay, so you converge somewhere.
So they just show that there is a convergence in the weak sense in terms of probabilities, where there are the two direct distribution, and so the noise can select U1 or U2.
Right, but the limit, does the limit depends on the modifier? So like for any modifier, you converge to the same limit. Is this correct? Or
here there is no modification, I think, for the first article.
Ah, okay.
They just show it's for me, it's more or less like a counter example that.
Oh, I see.
With this model, actually, I mean, all negative results are a very interesting result, and the answer are quite negative because you don't get uniqueness by zero noise limit or by modification. I think they say in the you know which one. They say the modification is not a selection principle. I think it's the title of the article.
Right. No, because it reminds me of like, you know, this maybe a little bit easier work of Landolli when he has like a very simple equation, gx equal root x, and already there the noise can you go in at the very maximal solution, a very minimal solution. But this is kind of okay, but this is still kind of nice. And then could you please go next?
Yes.
No, to your main result.
Okay.
So that we understand. And so now because this mild solution, so essentially it means that there is like one, so you say that something is a solution if you have one sequence of Bn converging to B such that corresponding Un converge to U, and then if you take a different sequence, maybe it will be like a different solution, right? So this is this is correct.
You mean that just means that this is the definition. That means that U converge towards older function, and B converge towards the true distribution.
Right. But then you take a different sequence of approximation, and then you might converge somewhere else. So this is you still allowed.
Okay. Yes. Okay. Yes.
I see.
It's a very weak notion of solution.
I see. Okay, so somehow you show that. Okay, so there is like a way to converge there. Sorry. Okay, and then what does your next theorem says? Because I didn't quite understand the difference between them when you talk about
the burger.
Yeah. So no. Sorry.
Okay. No. The two condition.
Sorry, I'm a bit confused. So you have this weak vanishing solution, and then you have another concept of solution, right? You have concepts of solution.
Weak solution.
Right.
If if U is a mild vanishing viscous solution, then it's also a weak solution if you can go to the limit in the weak formulation. That's all. Okay. The nasty part is obviously this part, and that there is a meaning of this thing thanks to the convolution, multiplication, and integration by the smooth function. It's you can obviously go to the strong formulation, and it's quite standard, it's quite usual weak formulation.
Right. Sorry, and then could you please remind us in the last my question be what you did for burgers exactly? So this is
the same thing actually, because in the control there is no dependency on B. Then I just use the same computation, replacing B by U in one dimension.
Okay.
We can go for more bigger dimension, but we have to give a meaning of this tensorial product. Just algebraic problem, and we get the same result, except here gamma has to be greater than 1/2 which is direct if you take a pen and write the condition when minus beta match with gamma. You obtain that in the previous theorem.
Okay, yeah, very good. Thank you very much for clarifying your presentation. Thank you very much. Yeah, so Andre.
Great. Thank you. Thanks for a great discussion and great responses. I open the floor to questions. Also, please, the presenters, feel free to ask each other questions. And for the audience, please just raise your hands and unmute. I will begin with two questions, hopefully to stimulate. For the last two presentations, firstly, for Lukas, I think it was, basically you constructed your analysis in a nonlinear Young integral framework. Could any, would it be impossible to construct it? Say there are other, I think, related frameworks. One could say Ito-Skorokhod and other a bit earlier frameworks. Could those also be used, or is this the best approach to proceed with your analysis? And secondly, for Igor, I apologize to both for interrupting you earlier, but as you see, we had to run with time. You analyze parabolic case. Could anything of your analysis make sense also in the elliptic case? For the elliptic equations, maybe I'm going outside of the box. You analyze it in the parabolic differential equation context, right? So would anything like this make sense with the viscosity that you use and turbulence concept that you implemented in the context of elliptic differential equations? Okay.
I don't know if I should answer first or if you...
Yes.
Okay, so I guess my answer is I'm not sure, but I would certainly not say that this nonlinear Young approach is the strongest approach you can think of. So I guess you, by applying stochastic suing, in most cases at least, you get better results. This is somehow, I mean, here I don't know what one can do, of course, but at least in our case, it's very specific using this non-negativity, and it's very restricted to the one-dimensional case where we get better results.
Mm-hmm.
But I don't know, maybe someone else would also want to comment.
Okay, thanks. Thank you. Maybe Igor? Yeah, thanks. You're muted, Igor. Igor, you're muted.
Igor, you're muted.
You're muted.
Sorry. You mean when you consider some converging in time when there is no more differentiation in time for the PD? Actually, it's not clear. Maybe we need to get some ergodicity criterion.
Yes.
In some sense, maybe we can do something. Actually, I don't know. It wasn't the main difficulty of the analysis. For fixed time, the nasty parts can work because you can overwhelm everybody. But for the main part, if you consider maybe very regular source function, actually, I'm very not sure. I'm really not sure. Maybe some sense, maybe very weak sense, maybe, but I'm not sure.
And this could then be applied to any parabolic your analysis equations. You analyze burgers, like Oleg mentioned. This can be extended to others, probably.
Although, I mean, it's applied for non-viscous burgers.
Sure.
What do you think about Euler equation or something
Maybe,
like this?
Or anything, yeah.
But for example, with Euler equation, there is a main difficulty because here I regularize the Gaussian, the each kernel density. But if you put a non-local term, which is the case for Euler equation, with the Honoré operator, there is a strange fact that you don't regularize only the it kernel, which can allows to pass to the limit when you go to 0. You regularize also the Honoré operator. So you have a term where there is no new contribution on new, but you are just regularize the Honoré operator, and this method actually things doesn't work with a non-local operator for this reason. And maybe other method, and maybe other method, actually it's future articles, I hope, to catch gamma equal to 1, which can get some uniqueness result. It's another speech.
Okay, thank you. Thanks for the reply. I hope also others that are still here could have any questions.
So maybe I have a follow-up question for Igor. So, okay, first of all, I just wanted to mention one other reference which could be of interest. Again, on the streak of negative results you mentioned, there is also one regarding actually non-uniqueness of vanishing viscosity solutions. So we'll just send it to the chat. But again, on this discussion on Euler and Navier-Stokes, but sorry, I see your point about the Honoré projector, but at the same time, I mean, couldn't you just keep the pressure? I mean, your theory should apply also when you have an external forcing term. So couldn't you try to actually treat the pressure as an external forcing and not apply the Honoré projector at all?
You mean just another representation of the Navier-Stokes equation or Euler equation?
I mean, the original one, because I mean, you know, the one with the projector is something you get afterwards.
It's quite a mess with that because, okay, if you know that the pressure is regular enough, that works. Okay. But for me, for the better, what I know, it's you get your pressure. For me, it's one of the most difficult parts of Navier-Stokes equation or Euler equation because it's mixed with the non-local operator. And if you explicitly write what is the pressure, you have the inverse of the Laplacian and so on. And this is inverse of the Laplacian who makes my Lukas trick doesn't work because that you know you have you regularize your its kernel with what is inside, thanks to the remainder term when you get a B delta and so on and so on. But if you have you add a non-local operator, the inverse Laplacian, that perturbate. No, I didn't success to mix the operator and to still regularize. So if we know that the pressure is regular, that works. But actually, I just know that there is some energy control by Honoré. That's all that I know.
Yeah. I mean, the known a priori estimates are poor. On that, I agree. Yes, the resolutions are not that nice. Okay, thanks.
You're welcome. Thank you for your question.
Any further question? Okay, if not, let's conclude. I greatly thank all the speakers, the great presentations, to Oleg for his organization and great discussion and everything, also to participants for the questions and involvement. I had so Firstly, this webinar, as I mentioned, was live streamed and recorded. It will be accessible on our channel in a few minutes time to watch them later. And we have 3 new webinars until the New Year time for us for this seminar. Most relevant is probably random matrices joined with anti-nulls, probably in December, and next one in October will be with jointly with Germain van Bever about statistical depth functions in non-parametric statistics, and in November with Bojana Milosevic about model specification tests, novelties here. So thanks again to all. I hope you continue to follow our work for more, I would say, probabilistic seminars in this framework and similar seminars. Thanks again to all, and hoping to see you soon on any similar event. Thank you.